So, any I will be able to see the participant. No? Yeah. Yeah. Hello students, welcome to this live session. If you have any query, you can ask me. No question ID. Yeah, but I will try to answer some of the previous questions. One question was spectrum estimation, that I did not cover because it was not in the syllabus, but spectrum estimation is quite involving, because to find out, suppose in the case of mean or this type of statistical estimation in time domain, they are comparatively easier. And one problem with spectrum estimation is that it is not consistent. So, even if we have more and more data, your estimation quality may not improve. That is why there are different techniques. It is a very spectrum estimation as a field, it is very old, and still methods are coming up because of its inherent problems. Anyway, we did not cover this topic because of the limited syllabus. Next question was how to choose the desired signal in adaptive filter. So, that is problem specific. So, for example, we have showed, suppose for system identification purpose. So, their desired signal is the output of the system, whatever system is there, that output of the system. Now, suppose if we want to suppress the noise, suppose in a loudspeaker you want to suppress the noise, then there will be additional speaker which will capture the noise, and that will be the desired signal. Now, in the case of MATLAB simulation, you can consider desired signal. Suppose if you have a sinusoid, that is your sinusoid plus noise, that is the signal you want to filter out, then you can consider a desired signal, suppose a delayed version of the sinusoid, that you can use as a desired signal. So, that way desired signal is always, you have to find out some form of the desired signal, either through estimation or through some prior knowledge of the signal. Is an effective noise reduction algorithm for speech signal for hearing aid? Okay. I think for noise reduction in hearing aid, that LMS algorithm is a good method. Like nowadays there is FLMS algorithm. Suppose how to clear that noise physically. So, there are methods like you can refer to the you can search in Google FX LMS algorithm, that is one of the practical method. And for speech signal, there are some other type of noise, it is not only white noise. So, those specific problem only speech related textbook will give you. Definitely, because normally when we have I am answering the question by Obilas, how to choose the filter length during simulation of LMS algorithm. Now, because suppose signal has non-linearity and you are trying to filter it by using a linear filter. So, the length of the linear filter will matter. Suppose if it is signal is simple signal, in that case maybe small length FIR filter will be sufficient, but if it is a complicated signal, in that case that length of the filter should be large. But again problem is like computational efficiency. So, that way you have to by trial and error you have to find a good length of the filter. You can see this, suppose in the case of simple sinusoid plus noise, and you can try with different FIR winner filter of length, suppose 5, 6 like that, and then you see how the performance improves. Okay, thank you. I am also happy to listen about you. okay, no, regarding your problem, maybe I can tell you later on. Rishikesh, because your compressive sensing based noise reduction algorithm for hearing aid. So, I have to look into it and then I will tell you. You write me a separate mail. Normally, when two random variables are independent, so suppose sources are different. Suppose you can say signal and noise. Signal is generated by one mechanism, noise is generated by another mechanism. Therefore, we can say that they are independent. My email address is available at my website. You look for Praveen Kumar Bora at IIT Guwahati. Email address is there. Regarding suppose two random variable, whether they are independent, actually independent by itself is a very complicated concept, because you have to see the suppose joint PDF and then find out the marginal PDFs, and if joint PDF is product of marginal PDFs, then you say that two random variables are independent. So, that way practically testing independence is difficult, but we assume when suppose signal, as I told, signal and noise case, signal and noise are independent simply because they come from two independent sources, and if causes are independent, that effects are also, we can say that they are independent. So, in that sense we can assume independence, but unlike independence, suppose uncorrelatedness, there you consider the covariance, and if covariance suppose is 0, then two random variables are uncorrelated, and covariance usually can be estimated easily, because it is suppose you can find out the mean of both random variables and then subtract and then find out the joint expectation, and this can be numerically done. So, that way testing uncorrelatedness numerically is easier compared to independence. So, look at my videos carefully, and it is sufficiently simple and elaborate. So that way I think many of the doubts you will be able to clear by re-looking the video, and if you have further question you can write me personally also. Yeah, that is right. Your question that whether we have to consider all the samples to determine the error, that is right. But there is that block LMS algorithm where you consider blocks of data. Suppose after a block of data you update the filter coefficient. So that way for for implementation efficiency there are methods, but the basic principle is for each sample you have to examine the error. Is it clear? There was another question, how to find MSC if you don't have the clear original signal. So, how to find out the MSC if you do not have the original signal. Now, this question because entire winner filter is based on that you have the information about the original signal, because this is a model. Suppose that according to that model, that the signal characteristics, at least second order statistics of the signal is available. So, that way and when we apply, suppose in practical situation in adaptive filter, for example, where we do not have the original signal, then we take the desired signal. So, that desired signal we have to find out from the mechanism or through modeling or different ways. It is problem specific. For each problem we have to find out what is the desired signal. But when we consider the model, in that case we know about the signal characteristics, statistical characteristics of the signal. That is why we are able to do filtering. So, suppose if x n does not, there is a question, if x n does not have 0 mean, then power spectrum will have an impulse at omega is equal to 0. So, that means if it is a non-zero mean, then there is a DC component. So, the signal has a DC component, and that because of that DC component, that autocorrelation will be always that there will be a constant autocorrelation, and therefore, its power spectrum will be a spike. So, that way at omega is equal to 0, there will be a impulse in the, that means that is DC frequency, that is omega is equal to 0 has a impulse, because power spectrum is density. If we integrate that, you will get the actual power. So, that way power spectral density, because power is constant and density will be, and it is at DC omega is equal to 0 and its density is that impulse. So, that way if it is a non-zero mean signal, there will be an impulse corresponding to 0 frequency, that is in the power spectral density. Is it okay? So, in that sense white noise will be always 0 mean, because its power spectrum is flat, but there may be non-zero mean white noise. In that case we have to subtract the mean and then we consider the white noise. Yeah, this question, yeah, because with each updated weight you filter the new sample. Suppose you have new signal has come, so you will filter the new signal with the updated filter coefficient, and then that error will be again determined, and that error will be used to update the filter coefficient, which will be used for next sample, filtering next sample. You remember that h of n plus 1 is based on the signal at x n. So, h of n plus 1, that filter will be determined from the signal at n. Is it okay? Because you suppose you have a filter, you use that filter to process the signal, and then error you determine, and that error is used to update the next filter weight. Practically, suppose one thing is model. Suppose question is practically how a PDF and joint PDF is obtained in the field. So, one thing is some model is there. So, those models are usually built over years, that is one aspect. Otherwise, you have to see the histogram. Suppose you have a histogram of the signal, then this histogram, suppose histogram, as you know, it is the plot of frequency versus amplitude. So, you amplitude you divide it into some bins, and then corresponding to each bin you determine the frequency, and as you make the bins smaller and smaller, then this histogram will approach the corresponding PDF. That is the assumption. So, that way you have to get the histogram, and then that histogram you can approximate by the PDF. And similarly, in the case of joint random variables, you can you will have to have the two-dimensional histogram, and that histogram you can approximate by some PDF, or that histogram itself you can assume to be the PDF. Of course, you have to normalize it, that suppose histogram, because PDF entire area is 1, therefore, to make the area equal to 1, you have to normalize the histogram. Suppose total number of frequency point, if we know that, you divide by each amplitude, you divide by that number, then you will get the normalized histogram, and which can be approximated as PDF. Is it clear? Okay. লিখিবলৈ okay, so So, you will have some histogram, you know, no? Histogram is suppose this is the suppose this is that amplitude of the signal, suppose these are the beans, okay, and then corresponding to each bin, suppose how many samples are in this bin, this is the one frequency. Similarly, how many are there in this bin, so this is the frequency, like that we can get this type of histogram. Suppose this is the histogram, and this histogram normally we will consider large number of samples, so that this becomes sufficiently smooth, and then this we can normalize. Suppose this is first interval, this is f1, this is f2, this is f3, f4, f5, f6. So, total number will be equal to summation fi. I is equal to suppose 1 to 6. So, we will divide each frequency by this number. Suppose if this is equal to n, then f1 by n, f2 by n, f3 by n, like that. So, this is the normalized histogram. So, we will get the normalized histogram. Now, when n is very large, this will be sufficiently smooth, so that we can consider it as a, suppose I can have a some PDF like this. Okay. So, that way we can approximate the normalized histogram when number of samples are sufficient large by the PDF. Next question is PDF is a function of random variable. So, now we know that this PDF is defined at a particular point. So, suppose a random variable is there at a particular point of that random variable, we determine the PDF. So, that way it is a function of that random variable. Suppose corresponding to every x we have a so here also I will just explain it to detail. So, suppose for every x I have f(x) of x, suppose this is f(x) of x. Now, this is also suppose corresponding to each x, random variable takes the value x, and correspondingly I have a PDF x. So, if I consider this x to be varying, then this will be also varying. So, that way this f(x) of x is a function of the random variable x, because you have to consider that x is varying. This x is a random quantity. If we consider, then this PDF is a also a function. PDF is as such, it is a function of this random variable, because you may consider that it is a deterministic function, but only thing is when this argument is changing. If we consider this argument to be a varying quantity, then it will become a random variable. So, that in that sense PDF is also a function of random variable. So, that concept for example, CDF that is fx of x. Now, when I consider this CDF of a function, so this quantity CDF of a random variable fx of x, so this is also a function of random variable, therefore, it will have some PDF. So, it can be shown that this function, particularly CDF, is always uniformly distributed. So, that way that principle is used, for example, in generating random variable, that you know the CDF of the any random variable, suppose CDF is uniformly distributed. So, you can generate the CDF and then use this mapping relationship, that is x and fx of x. So, inverse of that to generate the random number, that is one application. Similarly, in image processing there is something called histogram equalization. There also this concept is used, that CDF as a function of x is a function of a random variable. So, there is a question whether research present research areas related to SSP. Actually, SSP as a whole, it is a very big area, but it is more uses in application. So, that way if we consider as a theory, suppose as a theory statistical signal processing, then maybe research, maybe there are research like for example, higher order statistics, or how to estimate higher order statistics. This type of research are there similarly, but more research is in application. As you know that statistical signal processing, it is also known as time series analysis in statistics. So, that way time series, suppose we have different models, for example, ARMA, ERIMA, those type of models we have discussed, but practically suppose nonlinear situation, how to deal with. So, that way different type of concept, for example, cyclostationarity is one example, how to deal with signal which has some cyclic or periodic component. This type of researches are going on. Similarly, but one thing is that there is a thinking whether, for example, you consider even deep learning cases, like there are networks, there is something called LSTM network. Those type of networks also are example of application of extension of time series analysis. Whatever we try to do forecasting or predicting using time series or statistical signal processing, that is now in many situations, suppose neural networks are also doing that. So, in that sense, as such, what is the research area? Research areas will be specifically in mostly in application domain only, but there are some research in actual algorithm level, or like how to process different type of signals in, suppose when sample, for example, uniformly sampled, non-uniformly sampled, even compressed samples, those type of cases how to sample process those signals, there are research areas. Okay. Okay, next question is the bins in histogram will contain the sample value of the random signal. No, actually the bins will be like, suppose I will explain one example. Suppose you consider in the case of an image, again suppose you know that image, you consider the image has intensity from 0 to 255. So, 0 to 255, now suppose you have this intensity values 0 to 255, that you can divide it into maybe some 20 bins, suppose. So, this is 0 to suppose maybe 25, no 256 is okay, 16. So, 16, suppose 16 bins you consider 0 to 6, so that way 0 to 16 here, 16 to 32 here, like that. Now, these are the bins. Your amplitude, signal amplitude is from 0 to 255, and that you are dividing into 16 bins. So, that way 0 to 16 is 1 bin, 16 to 32 is 1 bin. Now, suppose you consider an image here. Suppose this is this intensity we are observing. This intensity is 255, suppose. Then this bin will be incremented by 1, and suppose next is 254. Then also this bin, suppose this last bin will be incremented by another one. This way, that way histogram will be built. Suppose here this is 0, this is suppose 25 only. Then this bin will be incremented by 1. So, that way you consider the amplitude of the signal, and then you are dividing it into bins, and which bin this amplitude will fall, that way, and that bin you increment. That way you determine the histogram. Okay. So, you cannot see the diagram to see. সৰু হোৱাৰ কাৰণে দেখা নাই নেকি? Yeah, suppose the diagram is like this. Suppose we have an image. You know that image intensity is 0 to 255, for example, gray level image, and this intensity you are dividing into 16 bins, 0 to, because there are 256 amplitude value. So, 16 bin. So, first bin will be 0 to 16. Now, how many intensities? Suppose this is the image, and now how many intensities are this bin? So, that frequency you will be putting here. Similarly, suppose 16 to 32 intensity. So, how many samples are there? So, that you will be putting here. So, that way we draw the histogram. Basically, you divide the entire amplitude into certain number of bins. So, intervals, they are called technically bins. So, 0 to 16 is one interval, 16 to 32 is another interval, and how many samples are there. Suppose this is the image, how many samples are there with values between 0 to 16, that number you put here. So, that way this side is frequency and this side is amplitude. Okay. Okay. এতিয়া দেখা পাইছে. Now, one question is why divide by n. So, this divide by n is to make that because PDF is suppose total number of, no, if we consider the PDF area is 1. So, that way that cumulative histogram value should be equal to 1. So, if you sum up all the histogram coordinate, then you should get 1. So, that is because it is a PDF. So, that is why it is normalized. Yeah, this is right. So, question is what is the difference between correlation and covariance. So, covariance is like correlation is a measure of similarity. So, you suppose you have a signal or random variable x, another random variable y. First you take the product and then you take the average. So, that is the definition of correlation. Now, first assume that there is a DC component, there is a DC signal. Then if we suppose x is DC, y is also DC, then their product will be DC means it is a deterministic quantity suppose. Then their product will be always fixed, and if we take the average value, that will be also fixed. So, that way there will be a similarity measure, but it is measuring the DC part only. So, this DC part will not tell you anything about the dynamics of this signal or random variable. That is why we subtract the mean from each of the random variable, and then again we take the correlation, that is the covariance. So, that way covariance you subtract the contribution because of the DC part or mean part, then you determine the similarity, that is the covariance. But this is the conceptually covariance means that, but it has interpretation. For example, the covariance also tells us how much suppose one random variable can be linearly determined in terms of the other random variable. So, that way covariance is degree of linear regression. So, that way also you can interpret covariance, but why you subtract mean, because DC part does not have any contribution to the dynamics of the signal. That is why you subtract the mean and then you take the correlation. Is it clear? Okay, then time is up, and okay. Okay, there is one more query, so I will explain that. Okay. Oh yeah. Suppose when we say correlation is, suppose x is a signal, y is a signal, you take the product. So, product for all possible values you take the product and then take the average, that is E of x y, that is the correlation. So, product for all values and take the average. Now, if there is a DC component, suppose if we have some dynamic part plus constant, suppose this is 0 mean part and this is some constant C1, and similarly y also y tilde plus C2. Now, if we take product, this is the DC part, this is the average part, this is the average part. Now, if I take the average value of this, we will always get suppose E of x tilde y tilde plus C1 C2, because this is a constant part and x tilde is a 0 mean. So, that way other terms will get cancelled. So, this part will always be there in the correlation, and this will not give you any information. Suppose you have a some signal value which is fluctuating about 5 volt and some signal value which is fluctuating about 7 volt. Now, this 5 and 7, they will always have some measure 5 into 7 which is be visible in correlation, but that will not tell about the fluctuating part. That is why we subtract it. Suppose when we subtract C1, that is E of x minus C1, that is the mean, into y minus C2. So, that way this fluctuation, this will now measure the similarity between the fluctuating part, not the constant part. So, that way this is the covariance. Okay. So, is it clear? Okay, then Sarat, bye. Okay. So, hope you enjoyed the course, and anyway exam will be as declared earlier, it will be objective type, and IIT Madras will declare the date, and you take care of yourself. Thank you.